Notes for 12.5, relationships between ellipses and circles. We've touched upon this a little bit in class, that there's definitely a strong connection between circles and ellipses. What we'd like to do is kind of strengthen that connection. So I'd like to start by looking at an ellipse on a graph. So I've got this ellipse, we got our focus points F1 and F2, major axis is on the x-axis, endpoints of A0, negative A0, B's, that should be 0B and 0, negative B. You'll notice that as my endpoints get closer and closer to being the same, whatever that might be, and it really doesn't matter which one it is, but as they get closer and closer to being the same, our ellipse becomes more circular in nature and comes very, very close to a circle. And in fact, when they are exactly the same, and it's very hard to get that exactly right on, when they're exactly the same though, we get a circle. And that circle is going to have a radius that is equal to A and B, because A and B will be equal to each other. And you'll notice that mine are a little bit off, and it's just more of a rounding thing than anything else here. But when they are equal, when your A value and B value are both equal, you have your ellipse becomes a circle. Okay? So here's what we have. As the foci of an ellipse get closer to the center, the ellipse becomes more rounded. When they are both at the center, the major and minor axes are equal and the ellipse is a circle. Therefore, a circle is a special ellipse. So really, we can think about a circle as being an ellipse, just a special one in which the A and B values are exactly the same. Okay? So if you want to think about ellipses as stretched circles is another way of thinking about it. Okay? If we do a scale change of HK is performed on a circle, if we do that, it will result in an ellipse. And let's take a look at this problem. It says, what is an equation for the image of the unit circle, which is x squared plus y squared equals 1, under a scale change of 9,5? So in other words, I'm going to take the unit circle, I'm going to stretch it 9 times as big horizontally and 5 times as big vertically. Okay? Well, let's go through what's going to happen if we do that. Okay? So I'm just going to show what I've done on that problem. So if I do a scale change of 9,5 on any point xy, it becomes 9x 5y. Okay, so if I have the point 1, 1, it would go to the point 9, 5. If I have a point 0, 2, it would go to 0, 10. Whatever the point is, we're going to multiply the x value by 9 and then multiply the y value by 5. Well, that means that x prime goes to 9x, and therefore if I solve that for x, that means x is equal to x prime over 9. And y prime is equal to 5y, therefore y is equal to y prime over 5. So if I replace x prime with x, okay, because it's my new x value, and y prime with y, I can say x over 9 squared plus y over 5 squared is equal to 1. And what I'm doing is I'm just taking these values here and substituting them in for x and y. So I'm taking that and substituting in for x, putting that and substituting in for y. If I do that, and then if I simplify that, I get x squared over 81 plus y squared over 25 equals 1. And you'll notice that that is an equation for an ellipse. So if you think about what happens in example 1 there, it leads to the following theorem. The circle scale change theorem, and that is the image of the unit circle with the equation x squared plus y squared equals 1 under any scale change, AB, A being the horizontal change, B being the vertical change, is an ellipse with the equation x squared over a squared plus y squared over b squared equals 1. Okay? It also leads to the graph scale change theorem, which is very similar to what we did with a when we did translations, okay? And that is, if I do a scale change, is the same as taking x out and replacing it with x over a, and taking y out and replacing it with y over b. Okay? So applying a scale change of AB has the exact same effect of doing what I did here in number 1. Okay? Now, the next thing that we have is a formula for finding the area of an ellipse. And the area of an ellipse with semi-major and semi-minor axis lengths of A and B would have an area of pi AB. So let's take a look at this example then. It says the statutory hall in the United States Capitol is an elliptical chamber. The gallery is 83 feet wide and 96 feet long. Find its floor area. Well, if it's 96 feet long, that would be 2a. That would be your major axis. So if I want to find the semi-major axis, that would be half of that. So I divide both sides by 2, so a would be equal to 48. And if the width is 83 feet, I can then say 2b is equal to 83, therefore b would be equal to 41.5. Now to find the area, I'm just going to take pi times a times b. So pi times 48 times 41.5, which is 6,258 square feet. And that would be the area of that gallery.